Right, welcome. Today we're going to be talking about something called titration. It is both a lab procedure and a formula that goes along with it. So for today's lesson, you're going to need a calculator. You're going to need reference tables. We're going to need reference table T, in addition to perhaps periodic table and table K and L for writing formulas of acids and bases. So first of all, a titration is a lab procedure that is used to determine the concentration of an unknown solution. And by unknown solution, I mean unknown molarity. So, for example, when you go to the store and you buy a bottle of vinegar, you don't know what the molarity is, the strength of that is. You know it's not going to burn your face off, but you also know it's going to sting if you have a paper cut. So the molarity must be somewhere in there. It's not nothing. So this is a procedure that is going to help us figure it out. In the titration lab that we do in class, we would use vinegar from the store, and we would figure out the molarity or the strength of it as compared to a base that we do know the molarity of. So what we do is we would use titration flask, Erlenmeyer. So what we would use, Erlenmeyer flask. This would be a ring stand. This is a special burette clamp. And this long structure here is called a burette. It looks like a very long, skinny graduated cylinder, except for it tapers off to a point, and it has a little valve right here. And it will be able to dispense the liquid either in a steady stream, or you can get it to go drop-wise. So we're trying to get this as accurate as possible, down to the drop or even half drop, to figure out how much it's going to take to get to what we call an end point. End point is when acid and base come together and they are going to have equivalent moles. So we're not going to say neutralize necessarily, but equivalent number of moles. Burette is also sometimes spelled like this, sometimes with an ETTE. Either one would be acceptable. So it's a lab procedure, but there's also a formula that goes along with it. So if you could go to reference table T, you will see that titration is the third from the last one. So we're dealing with molarity of H plus, acid, VA, volume of acid, molarity of the hydroxide or base, and the volume of base. Now, you can't see this very well down here, but my formula is a little different because the Regents has taken off something that we should definitely talk about. And it has to do with something called equivalences. Anyways, we'll get to that in a second. So we'll talk about how this is going to be affecting us in the honors class and why it's not on the reference table anymore. So if we were to do this lab, we would take a volume of an unknown molarity of acid. I mean, I know what the acid is. I'm picking it up from the store and putting it in my lab. Usually we would use acetic acid. You could use HCl hydrochloric, but I don't know how strong that is. We would need to add 2 to 3 drops of an indicator solution. Now, if you don't remember what those indicators are, they're on table M. The one we generally tend to use during acid-base titration is phenolphthalein. It's that crazy looking word. It starts off colorless and then it turns pink when you get to that end point. So the flask would have the acid. The base would go in that burette. And that's how I always remember it, base burette. You could certainly do it the other way, but we just need to know how much comes out for that. So we're going to add the base from the burette slowly until you see a color change. So what we would normally do is we'd let it go out fast in a steady stream, and you'd notice it turned pink, and then it would go away. And then it would stay longer pink, but still go away until finally the pink remains for the while. So here we have a diagram, and this kind of very faint pink is what you want. The darker magenta you get means it's no longer right at that middle ground. You've gone too far into the basic range. So we want the most faint pink you could get that remains. If it's very, very faint, but then eventually fades to nothing, that means you're not there. You're not at this absolute middle point, what we call the endpoint. So I want you to take a look at how this formula is different than on the reference table. The reference table did not include something called the H plus equivalence and the hydroxide or OH minus equivalence, but I did. Let's talk about what that means. This, I don't believe, is in your notes. I apologize. You can add this in the margin, or you can put this on another sheet of paper. Another page is blank. But this should just kind of clarify what equivalences are. So sometimes you have acids that are diprotic, di meaning two. So these acids are going to give off 2 hydrogens per every molecule in solution when it ionizes. So in our calculation, we need to account for that. So we'd multiply our molarity and our volume by a 2. So what are examples of diprotic acids? So let's take a look on table K. Diprotic acids would have 2 hydrogens. So that would be sulfurous acid, sulfuric acid, carbonic acid. Okay, so these, because they all have 2's right here, those are going to have a 2 of equivalence. So what do I mean by that? So let's take this sulfurous acid. Let's break it down. Let's ionize it. It's going to break apart into H plus and the sulfite. So sulfite has a charge of -2. If you didn't know that, it's on table E. But look here, if it gives off 2 hydrogens, there are 2 hydrogen ions. So our equivalence is a 2. This might seem sort of familiar, like the Van Hoff factor we talked about in solutions, which raises the calculation of our boiling points and lowers the freezing point depressions. Similar idea, but those are for ionic solutes, and this is for covalently bonded or molecular solutes. We also have something called a triprotic acid, prot meaning proton. So triprotic can donate 3 H plus. Of course, that's right in the way. So for example, we have phosphoric acid. Looking on table K, it doesn't look like we have any other triprotic acids, but if you think about it, this is going to give off H plus and the phosphate. This is -3. Notice that if it's going to have 3 hydrogens, they're going to be given off. So our H plus equivalence would be 3. So we would use this number when we do calculations of titration. But this, oh, and by the way, what about things like HCl? HCl, how would that break apart? That would break apart into H plus and Cl minus. So what kind of an acid is that? That would be a monoprotic acid. And you would include a 1 in your calculations, which of course doesn't make any difference mathematically, but might be a good practice to include it, because then it shows that you understand that when it dissociates or ionizes, it's going to still give off just that 1 proton. This also will affect bases. They just won't be called diprotic or triprotic. They'll be called dihydroxy or trihydroxy. Dihydroxy, 2 hydroxides. So again, the same idea goes. In the calculation, you would include a 2. So it's not just Ma times Va equals Mb times Vb. If you have a dihydroxy base, you would multiply the base side by 2. So for example, dihydroxy bases, one of them is calcium hydroxide. That's the only dihydroxy base on table L, but of course anything from group 2 like magnesium, any of those, barium, those would all have dihydroxy bases. So when this is breaking apart, we're going to have our Ca plus 2. We're going to have our hydroxide, which is -1, but notice there are 2 of them. So there would be 2 hydroxides, meaning your equivalence is a 2. That 2 would be multiplied by the molarity of the base and the volume of the base in our calculation. Same idea with trihydroxy. So here I have aluminum hydroxide. Sorry, you can't see that, of course. So that would break apart into the Al plus 3 and OH minus. There are 3 of them, so 3 OHs. So any kind of calculations you would do, you would multiply that side by 3. And just like before, if you have something like sodium hydroxide, one of our favorite bases to use, when sodium hydroxide ionizes in solution, it's going to give off Na plus and OH minus. It's only going to give off one OH, so what do we call that? We're going to call that a monohydroxy base. And so that would not affect our math in any way. So the question remains, why on the reagents did they not include the equivalences? Well, it's because the reagents doesn't think that you can understand that. So they're going to always make sure that every acid and base that neutralizes in a titration is going to have the same equivalence. So they're either going to have both monoprotic and monohydroxy substances, or they're going to have a diprotic and a dihydroxy, or a tri, and so forth. So you're not going to need to use this on the reagents. They're always going to be 1-to-1. But I guarantee you that in my calculations, they will not be, because I want to make sure you're paying attention. So if you'd like, I would take reference table T and I would add H plus equivalence and OH minus equivalence to the formula for titration. Wouldn't hurt. Even if you just put in a 1 and a 1 and they cancel out mathematically, or a 2 and a 2, at least you'll have that there going forward. So let's take a look at some titration data. So first of all, we know the concentration of our base. We know it's 0.5 molar. We don't know the concentration of our acid. By the way, how do you know who's an acid and who's a base? How about you check table K and L, and if you still don't know, who's giving off H plus? H pluses are acids. Who's giving off hydroxide? OH minus, that's base. So here we have our formula. This is the part that's on the reference table. Whoops, not this part. But we included the equivalences. So we have our original volume of our acid. This goes in the flask. And we have 10, I'm guessing milliliters. And I should have put a 0.0 because you would go to the tens place. So when you take your initial volume of the burette, it was 21.5 milliliters. Here's something else I didn't mention about burettes. Burettes, which contrary to most grad cylinders, that's clearly the valve here. Sorry. So we start with 0 up here, and we start with 50 down here. Now, usually you're used to 0 at the bottom and a large number on top. Doesn't really matter, does it? Because you're always going to find where you start and where you end and take the difference. We're just going to find how much was used. So it's just how bases or how burettes are made. So we're going to start with our initial base volume of 21.5 milliliters. You're going to add base, add base, add base until finally the solution in the flask turns pink. We're using phenolphthalein as our indicator. And when you are at that pink that remains, you take the volume of your burette and it's 33.6. So to figure out how much you used, just like finding a delta T or any of those, it's final minus initial. So we used 12.1 milliliters of base. So now let's plug this into the equation. We'll start off with what is easier. So our molarity of the acid, that's what we don't know. That's going to remain our variable. Then we need to look for the volume of the acid. Well, 10 milliliters. The molarity of the base was given to us, 0.5 molar. The volume of the base, how much did we use? It was 12.1 milliliters. You know what? I'm going to make these parentheses just to keep things a little bit neater. Okay, now let's look back to see which acid and which base we used. Because if you notice, these are not going to have the same amount of equivalences. So over here, I'll do some calculations. So we have H2SO4, that's sulfuric acid. How is that going to break apart or ionize? It's going to give off H+, but there are 2 of them. And it's going to give off sulfate. So that 2 needs to come into our equation. There it is. That's our equivalence. Take a look at your sodium hydroxide. Now, you don't need to show me this work every time, but it does help you kind of see the process. So notice that there's only one hydroxide ion given off. This is a monohydroxy base. So I'm going to put the 1 in here. Mathematically, you know that doesn't matter, but I'm going to put that in there anyways, just so you can see it. All right, so then we just do some algebra. 0.5 times 12.1 times 1 is 6.05 here on the right. And we're going to have 10 times 2, which is 20, times whatever the molarity of the acid is. Divide both sides by 20. Divide both sides by 20. Gone. So that divided by 20. All right. So let me see. Yeah. So then that means molarity of the acid is this. So at first I did not know, and then I did know. And that's what it is. By the way, if any of these calculations don't seem right because I'm making a mistake on the fly, I do apologize. You should always double check me. And finally, we have our acid-base reactions. So you should be familiar with things like synthesis, decomposition, single replacement, double replacement, combustion, that kind of stuff. These are specific to acids and bases. I wouldn't consider them brand new reactions. They're just specific cases. And our first is called neutralization. It's a specific kind of double replacement. So you should remember in a double replacement, you have two compounds, positives and negatives. Positives will switch. And in this case, we have an acid and a base, which will always produce a salt and water. Salt is ionic compound. Water, of course, H2O. So let's give this a try. Acid, base. So this is H plus, Cl minus, Na plus, OH minus. Double replacement, we're going to switch the positives. So Na is going to be with Cl now. And make sure you check your charges. This is a plus one, this is a minus one, so we're all set. H is going to be with OH now. And there's another way you could write that. It'd be H2O. So in this case, the salt is sodium chloride. Do I need to balance for coefficients? No, I'm good. Here's a trickier one. So once again, we're going to do switching of the positive. So aluminum, which is a plus 3, is going to be with sulfate, minus 2. And so we're going to crisscross our charges. So that means that the 2 from sulfate comes down here. The 3 from the aluminum comes down here. And we still have H2O. Always water. Always. Now you just need to go back and balance this thing for coefficients. Should we do it? Let's see. Let's put a 3 there. Take care of our sulfates. We need a 2 here for the aluminums. Now there's H's and O's all over the place. Let's see. We've got 6. And 6 is 12 hydrogens. So how about a 6 here? Let's hope that does it. So we've got 12 and 6. 12 and 6, 18. So there's 6 and 12. Yep, we're all set here. So a neutralization reaction is when you have an acid and a base producing a salt and water. Now, I think everybody associates sodium chloride with salt, but aluminum sulfate is also a salt because it's an ionic compound. Speaking of salts, we have something called hydrolysis of salts. This is not in the Regents anymore, so this is honors only. So if you've got what we call a strong acid or a weak acid, strong base, weak base, that's on honors reference table L, I think? That Ka table. Yep, table L in the honors section. So if you put a strong acid together with a weak base, that is going to produce a salt that is still slightly acidic because you know water is neutral. So the salt is going to pick up some of that leftover acidity. Strong base and weak acid will produce a basic salt. So the salt will pick up some of that alkalinity or basic character. Two strongs is going to produce a neutral salt. And by the way, how do I know what a strong acid is? That would be high on honors reference table L. So something like, it's Something like hydrochloric acid, hydrobromic acid, or hydroiodic. So 2 strongs is neutral. 2 weaks, we don't know. It really depends on the conditions. So there is a lot more we could do with this, but honestly, we're not going to. Be prepared for it in SUPA or AP or college. But I just wanted to give you the idea that you can't just throw any acid and base together and make it totally neutral. You're going to have a remnant of whatever's left over in your salt. Finally, single replacement. You should be familiar with this already, but this time we're using specifically an acid. So remember, with single replacement, you have to use reference table J, the activity series. So only if your singleton is more active than whatever it wants to replace can it go forward. So you have a metal plus an acid producing a salt and hydrogen gas. So for example, this is one that we actually did in class. So we've got magnesium, which is a metal. So we're going to try to replace H, which is not truly a metal, but it acts like a metal according to table J because it gives off protons, etc. Anyways, it gives off electrons, excuse me. So is magnesium higher than hydrogen on table J? It is, which means hydrogen gets bumped out. Oh wait, alone, it must be diatomic, H2. And then we've got Mg plus 2, Cl minus 1, and then balance her out. So here we go. So that's a specific acid-base reaction. Okay, and that's it for today. And by the way, I don't know, I have this lingering feeling that this calculation I screwed up. Double check your math on that one for me. All right, thanks for watching. Take care.